Good afternoon. Welcome to our Thursday afternoon colloquium series. It's my pleasure to introduce Dr. David Su. I have known David for more than 20 years. He used to work at a company called Energy Conversion Devices, or ECD, in Troy, Michigan. Stanford Ovshinsky had started the company, and they were working on several very interesting, very innovative technologies. Solar cells, batteries, data storage, media. And I remember when I visited, my host was Dr. David Strand. And I walked in, and I was introduced to people. One of them was David Su. There was another David. There was another David. And I said, is everyone here called David? And they said, yep, that's what the name of the company implies. ECD means everyone called Dave. So anyway, so Dave worked on spectroscopy. He was the chief spectroscopist at ECD. He did a lot of interesting work there. And he claims to have touched a quarter of all the elements in the periodic table. I hope he has not touched the dangerous ones, like, what are they, beryllium and uranium, radium, mercury. But after leaving ECD in 2007, he started his own company. Then after a couple of years, he joined another startup, and he's working on solar technology, solar energy technology. He's going to tell us about it today. Thanks, Dave.
Thank you so much for inviting me to talk to all of you. I got to say that Mesut is one of the fine gentlemen out there that I know, and I hope you all appreciate him, because I do. Yeah. So I am a spectroscopist by trade, and we're going to learn in the first part of my talk really what that means. Any of you want to give me your own definition of what spectroscopy is? Come on. Hands? Anybody? Yeah.
Rainbow in the electromagnetic wave.
Okay. Anybody else? So I'm going to start off with a kind of a strange question, and I want to ask, so bear with me a little bit. Who knows who Isaac Asimov is? Hands raised, huh? Okay, maybe a half of. All right, now, a follow-up question to that. Who knows what a robot is? Okay. So those of you who don't know who Isaac Asimov is, the word robot comes from Isaac Asimov. Okay? And he was the one who really understood what robots do and what they should never do. Who knows what the 3 laws of robotics is? Well, tell me, what are they?
Well, issued by Asimov is a robot should never harm a human being. Robot should never take action.
So that's number 1. Number 2 is a robot should always obey humans, with the exception of if it violates number 1. And the third one is a robot should not harm itself, with the exception that if it violates 1 or 2. So in our present technology, a lot of folks are talking about artificial intelligence. Anybody working in this field? Anybody? Anybody who knows someone who's working in that? Okay. So what I would like you to do is the next time you see them, first of all, ask them if they understand what the rules of robotics is. And if they don't know what the rules of robotics is, in my opinion, they should stop what they're doing, because it is that important to our future. Now, what Asimov does is in his first book, Humans Find Exoplanets. We're really close to that right now. We're finding thousands of exoplanets. Humans send robots out to prepare for the arrival of humans. Humans get there, and they discover that there's a big problem. They cannot live with robots. So the humans revolt against the robots, destroy all of them. Sounds like science fiction? In 1950, when he wrote that, that's science fiction. Today, it's sounding like science fact. So, why all this talk about Isaac Asimov? Well, I was reading this book, a collection of his short stories, and one of his short stories is called The Bridge of the Gods. What's the Bridge of the Gods? All right. After I talk about that, I'm going to talk about my work in scattering, and I want to see if we can use scattering to understand some fundamentals about what's going on in cosmology. But let's start about scattering, spectroscopy first. So the Greeks thought that color was a property of the material. Gray, I can touch it. Beige, I can touch it. Apple, I can touch it and eat it. And then people say, well, what about a rainbow? I can't touch that. But you're not looking at the whole picture, okay? If you were Zeus or any of the other gods, how do you get from the heavens to earth? You walk on a rainbow from heaven to earth. So if you were a god, you could touch it. You do it all the time, you see. So that was the Greek understanding of what color is. Well, jump 2,000 years later, Isaac Newton comes along, publishes in Optic, and he essentially does this experiment, shown there. White light, prism breaks it up to color, puts a lens in there, goes back to white light. He says color is a spectrum. Now, it's a very strange word. And of all the words he could use to define what he has seen, he uses the word spectrum. He gives us that word. Why? He puts his hand in here. Hey, I see it, but I can't feel it. I can't touch it. Therefore, he gives us the word spectrum. Now, I want to make very clear to you that he's not saying all these colors together make a spectrum. Every single color is individually a spectrum. So if you could give us an ideal, true, single wavelength light, as good or better than the best lasers that we have, that light itself would be a spectrum. Really? Well, that's what Newton says. Why? The word spectrum is the Latin for apparition, meaning ghost. Can you imagine? Out of all the words that he could have chosen to describe what he sees, he chooses that word, which means ghost. So my wife is from Mexico. Anybody know what that is? La Virgen, Guadalupe. You go 50 miles south of here. Every single person in Mexico knows what that is. After the conquest of Mexico, the priests and the monks tried to convert to Christianity. Mexico failed miserably, utterly miserable. She comes along, and within weeks, the whole of Mexico was transformed. Whether you believe it or not has nothing to do with reality. This happened, and it changed Mexico. And Mexico is Catholic because of this. Spectroscopy in our lives is just as important. It has transformed physics and astronomy to such a degree as powerful as this. Well, Maxwell comes along. So much of what we learn about Maxwell is, okay, he unified the electrical and the magnetics. But what we don't talk about Maxwell is he unified light and matter. All those terms involving current and charge. Well, that's matter. Without that, Maxwell's equations are boring. Nothing exciting. But all the physics, important stuff that we do today is because of light and matter. And that's what Maxwell did. So it seems like, hey, maybe the Greeks were right. We've come full circle. Well, not quite. You see, to quantify color, 3 things are important, 2 of which are physics. The object and the illumination source. The other is physiological. The Greeks and Newton had no idea of this understanding. Well, in the 1930s, scientists finally started looking into this matter. So today, this is called the chromaticity plot. And if you say that color is related to wavelength, you are right as long as that wavelength and color is exactly on this curve here. Anywhere else on here has nothing to do with wavelength. This whole thing over here, this is called the line of purples, nothing to do with wavelength. You cannot build a laser beam having a single wavelength of this color or this color, magenta. You cannot do it. It's impossible. Why? It's not physics, it's physiology. Now, just to prove to you what's going on, I have a wavelength here and a wavelength there, and if I've adjusted the intensities like this at that spot. And over here and over here, another adjustment of intensities. This is called metamerism. And these are the colors of each of these spots over here, but they all give the same color. One color has an infinite amount of different wavelengths that you can combine to give it that color. So forget that color spectroscopy means the study of color. It does not. But the reason we say it is because spectroscopy is the study of the wavelength dependence. It's too much for the mouth to handle. So that's why we say, well, spectroscopy is the study of color. But now, the question is, why don't we teach this in our curriculum? And the problem is, my boss says, David, we're building this device, and I want it to be color neutral. Oh, I had to go out and learn all this stuff. Not in one single book that I had in the physics literature, in the physics curriculum, could I go back and open it up to learn about this. I had to learn it all about. But color was important in science. Now let me give you a prime example of that. Hertzberg-Russell chart here. Intensity, our sun here, intensity ratio relative to our sun is right here. B minus V. These are magnitude, blue, and visual. Okay? 1910. At that time, there was no solid state sensor. There was no color film. There was no nothing but the eye. And they did all of their great science because of the eye. So, understanding how the eye works should be an important thing in physics. But we ignore it. Well, guess what? Richard Feynman has 2 chapters on the eye. Ha! Saved the day in my book. So, the thing about it is, at one time, physicists were saying, astronomers, you don't understand the way suns work because we're measuring the number of neutrinos coming out of our sun, and it's about 1/3 lower than we expect based on your models. And so I think you guys don't really understand the way suns work. The astronomers say, Mr. Physicist, I don't think you understand the way neutrinos work. If the physics community understood this chart, they would have never said that statement. We know, based on the way this is the main sequence, The blue stars die off quickly, and this goes that way. These are dying stars. Okay? They can model this exactly. Right? Where's Mr. Park? Mr. Kim, I think it was. Anyway, they can measure this exactly. Okay? 1910, they already, in my book, this is probably the top 5 achievements in the whole of astronomy, this chart right here. Okay? All right, so in conclusion about spectroscopy, Richard Feynman says color is not a question of physics. It is a question of light itself, and the color is a sensation. It's a sensation. Our brain creates it. So, Isaac Newton was right all along. Color is not real. It is a ghost. It is therefore a spectrum. I found this out by reading this book. Isaac Asimov is one of the most important science communicator that we have ever had. And I learned it from him, not from any of my physics curriculum. I was so excited about this learning, I ran up to my wife and said, "Hey, Letty, guess what? I've been studying ghosts for the last 30 years of my life." Okay, whatever you say. All right, so let's move on to my real work today, is talking about scattering. And why am I interested in scattering? So it really gets down to, we're building a window product based on polymers. And the problem with polymers is it has a certain amount of haze into it. Haze makes it look a little bit milky, a little bit bluish, scattering things. And you know, the thing about it is, us scientists and engineers, we always think, hey, I've got the greatest thing in the world. But guess what? You put that product on display, people like what they like, and they don't like what they don't like. You try to sell them that, you will be largely disappointed. We have to solve this problem. It is a huge problem. We are trying to use polymers in our substrate, and they have medium haze, and we would like it to get up to a low haze thing. There are other folks using nanoparticles to design very high insulating power materials. Okay? They have high phase, 10%. They're in a heap of trouble to try to do that. So the question is, how do we get it? What is the mechanism causing haze? And the thing is, I don't have an immense laboratory research of a university to go to. I just have a little spectrometer. I got to do that all on a little spectrometer. Well, when I was at ECD, one of the things to know about energy conversion devices is they are one of the places that first really asserted that amorphous materials can have useful properties, electronic properties, optical properties, and so on like that. And I was trying to understand amorphous silicon. So I picked up this book. If anyone wants to study scattering, the first book that you should buy is this book by van der Hulst. In the 1930s and 40s, he was the one who really understood interstellar medium. All the gas, the little dust particles are out there, and he even predicted that the atomic hydrogen 21 centimeter line could be observed. And 10 years later, they found it. So now if you want to know how we know where atomic hydrogen is, it's all because of van der Hulst and this 21 centimeter line. So all the formulas that I use in my work today came from this book. Yeah? But I don't use them in ways that people typically use those formulas. And so what I'm trying to do is just to describe, we're going to be looking at power laws. I call it parametric power laws because it's just a parameter. I'm going to apply that to all my data. I'm going to apply the same thing to all the theories. Okay? So, you know, the problem, whenever you want to understand something, you have an experiment, you have theory, and you have to kind of match theory with experiment. And so the question is, well, what measurement do I do? And what theory do I use? How do I understand that? And sometimes the theory is so damn complicated, it's like, well, gee, you know, that's not easy. And the thing is, for me, in my little laboratory, I've just got to, I've got to do this in a simple way. So the question is, can we use an integrating sphere to get meaningful information? I'm going to describe that a little bit later, what an integrating sphere is. So basically what I'm going to do is be measuring the power laws by experiment of our samples. Okay? If the power law is 4, that's Rayleigh scattering. If it's not 4, if it's 3.9, 3.95, it ain't Rayleigh scattering. It's Rayleigh-Gans. It's okay. I'm going to come to that in a second. So let me just say that we're going to use a dual beam spectrophotometer and forward scattering. We're going to measure the diffuse forward scattering by an integrating sphere over those wavelengths and so on like that. Okay? White clouds are white because there's no wavelength information. They all scatter in similar ways. So there's no power law at all. And what we're going to do is just like this is a power series, we're going to call all of this the same power series, power law. Rayleigh scattering, like I said, is 4.0 power law. If it's 3.9, it's Rayleigh-Gans scattering. If it's 3.0, if it's 2.0, it's still Rayleigh-Gans scattering. After a while, you can't use that anymore, so you have to go to Mie scattering. Okay? So what I'm going to do is treat theory just like I'm treating experiment. Force everything to fit to some kind of power law. So I wrote a paper on this, and if you want to learn more about the nitty-gritty details, just look me up on Google and you can find it, okay? I don't want to get into all the details. But one of the things that I had to do was make sure that I understood that all these things behaved well and conservation of energy behaved well and all that. So you know, it's not trivial to make sure that we understand that that's true. So at the end of the day, we come with a formula like this. Light comes in, it kind of bounces around. There's a specular part that comes out. The scattered part, you can think of this as an integrating sphere. Some of that scattered light goes forward, some of it goes backward, and so on like that. And so we can model this like that, and under conditions of small scattering extinction or small thickness, that exponential becomes a simple thing and it factors out, so you can get an expression like that for the scattering. Now, in the scattering theory, they don't talk about cross-section. Physics people always talk about cross-section. What the scattering folks do is they factor out the physical dimension of the scattering center, and then they assign a scattering efficiency to it. So all the modeling is to say, what does that look like? What that big Q looks like. Okay? Now, if you want to integrate all the loss, you can come out with what this extinction coefficient is. It's the area times this efficiency factor, and then you see the number density is in there. And then since I made the measurement up there, you see, now I can start making sense of my data. Now, experimentally, you're going to have something in there that are large scattering center. They have no wavelength information. So that's large, and I call that a constant, like a DC term. Then there's going to be a small scattering centers that have wavelength dependence. Okay, so that K there is really the wave number. Thank you. So this A here is an amplitude-like term, right? The amplitude term has the number density in it, but it also has the efficiency factor. It has all that other stuff in it. So how do we get all of that? Okay, so when you combine all these terms over here, the theory, like I said, is what we're going to do is calculate that according to every theory. And then we're going to say, okay, I'm going to fit that to the same kind of power law expression as I'm doing up there. And instead of this big Q, I'm just going to give my own little Q there. And once I have this, it's going to turn out that once you measure the power law, that uniquely gives you the size. Once you know the size, you know the efficiency factors, and this is the measured term, and this is the radius, but this is the radius in the same dimensions as your measurement. So if you do nanometers, this is nanometers. And then this is a radius, the same radius as that, but this is in maybe centimeters or meters, whatever your thickness is. So you can uniquely get the number density out. Okay, so let's look at how the fits go for the theory.
Can you go back to the previous slide?
Mm-hmm.
How do you know which regime of scattering you're working in? How do you know if it's Rayleigh or
Do you remember Rayleigh-Gans scattering is between a power law of 4 and 2, and between 2 and 0 is me.
So you just, by fitting, you find it.
So I'm gonna answer your questions quickly. Okay? So you take the me theory, you take the Rayleigh-Gans theory, you give it a size, and you plot the scattering thing as a function of x here. This is dimensionless quantity. This L is wavelength. This is the size. And you see, holy cow, I got two different curves. But now these circles over here, these are all the fits, the power law fits. Okay? It's not perfect, but it ain't bad. But you see, the power laws are different. What the heck is going on with that? When I first started this, I thought, hey, this is going to be easy. I'm just going to do that. In one range, it's going to be Rayleigh-Gans, and the other range is going to be me theory. Just lickety-spit, I got the answer. Then this kind of stuff happens. Whew. All right. What's going on? Let's look at this some more. Suppose rather than 30 nanometers for these samples, I increase it to, say, 250 nanometers. And now the me theory is starting to give this. So I'm trying to fit this crazy thing by a power law, and it doesn't look very good, but the thing is, it's an effective thing. Usually when we study scattering, it's at a single wavelength. We do lasers. But we don't have mono-dispersed particle size. When you have a crazy sample, it has sizes of all kind of things. And so it's really in the incoherent regime. Okay? So this curve is not really even right because it assumes a single wavelength and everything is coherent. Now, when we make it even bigger, close to 1 micron, it starts to flatten out like this. And if it's even bigger and bigger and bigger than that, it just goes to this 2. Now, when samples are really big, why does the efficiency factor go to 2? Anyone want to guess? So, the first factor of 1 is a particle this size, the light comes in here and is scattered away. Okay, so if you have a detector over here, that's one factor. But if you have but there's another thing going on, that's called diffraction. So a particle this size, even if there's nothing here, all the light on this edge diffracts away. Okay? And the amount of that diffraction away business is dependent upon the size. So that's why this eventually goes to 2. But it goes higher than this because there's interference going on within the particle and all kind of things like that. So that's why it goes up to 2. So even though these things look like that, we can still assign it an effective power law in the Me regime. Now let's look at our data. Okay, this is real data now from a real polymer. And I can't tell you what that is because we're still working on this. And when you work for a little company, you can't tell people what you're doing. But I can show you data, and it's still pretty interesting. So I'm not telling you what it is, but this is what it is. So this is a fit, and this little thing, this is the large component of the scattering. And these have power laws, and you can see how good the fit is. So what we do is we measure between 190 nanometers wavelength. Every 1 nanometer we go up all the way to 2,500 nanometers, and then we plot the wave number like that, okay? And this is the exact data from our integrating sphere. These similar power laws. Some of the difference in here is related to the power laws. Some of the difference is related to the amplitude term. Then we process the data. Things change. The power laws are changing. The amplitudes are changing. Another set of data, kind of similar thing. Another set of data, kind of similar thing. So the lines are our measurements, and the dots, they are the fits. Okay, and these fits are so good. I do chi-square analysis on them to minimize the fit. So when we combine all of this, whatever the process condition that we vary, we know the size, and therefore we can calculate the scattering area. And we also know what the number density is. And therefore, knowing the size and the number density, we can calculate the total scattering of everything in the sample as an area. And notice, one of the interesting things is okay, E1, E0, that's 1. So we're actually scattering more than the physical area. So if this is the physical area, all the scattering elements add up to more surface area than the actual sample here. So when we do that, the amazing thing is we get correlation coefficients of 0.96, it's like, holy cow, this works. And, even though I came up with this strategy, I'm always thinking, yeah, but does it really work, and why should it work? But, why should it not work? Things are changing. And things change in a regular way. So down here, what I do is I take all that data and I plot the number density versus the radius, and you can see the type of radiuses radii that we are talking about here. All these different samples are on the same curve over here. There's a lot of physics in that. Why is that happening? So what's happening is we start up here, we process it. The number is going down, but the radius is increasing. You see? So whatever's going on, whatever the meaning of radius means or size is, the number is going down and the size is going up. Ha! We're coalescing. This is kind of a coalescing. Okay? So, something really powerful is here, even though the analysis is very simple. And so, rather than saying this sample has a certain Haze value and this sample has a different Haze value, okay, why? Well, now I can tell you why. It's because the number is changing and the radius of the scattering center is changing. I'm going to get to your question in a real second here. There's a big problem, however. All of this stuff up here is in terms of atomic theory of matter. All of the stuff down here, is in terms of continuous theory of matter. guess what? We don't have a physics that joins these two in a natural way. All this stuff here, this is 100-year-old physics. Okay? We are still using concepts from 100, 200 years ago in our formulas today, and when we come to nanometer scale size, we're expecting that that works. Okay, so now let me answer your question, Mesut. So this is what I do. This is the Rayleigh scattering point right there. All these other points here is Rayleigh-Gans scattering. And here, this is me scattering. What happens is, when I measure a power law, I come over here, I measure the power law, come down here, boom, this is a log plot. I uniquely get the radius. But guess what? There's a problem in the middle. What happens if I had a 1.9, which I think I showed you previously? What the heck do I do? Now, part of the me thing, you have to put refractive index in there. If I have 1.2, this whole thing shifts over. 1.1, it shifts over more. 1.4, it shifts over this way. 1.5, even more. But you know, darn it, physics has to have beauty in it. If I go down here and then this guy is moving all over the place, that's not beautiful, that's ugly. So what I do, it's a cheat, I admit. I say, okay, the thing that makes this curve and that curve line up is at this refractive index for the me calculations. And then what I do is I take the most steepest point over here and the most steepest point over here, and I draw a line over there, and I said, anything in here is this line. So that's what I do. You don't like it? Okay, I don't like it either. But what else am I going to do? All right? We don't have a unified scattering theory. So now that I have the power law and I have the radius, then all these other terms over here, these are the efficiency-like scattering terms. So now I have those too. Okay? But, you know, so look, this is about 100 nanometers and this is about 30 nanometers. So anyone who's working on objects that are between 30 nanometers and 100 nanometers, and you're doing so-called rigorous calculations using Maxwell's.
You say draw a line, you mean draw a line on the log scale?
Exactly. Exactly. I tried to do it in a linear scale. It doesn't look pretty in a linear scale. Once I have this line in a log scale, then I convert this back to linear. The slope, it looks beautifully continuous on a linear. So that's correct. Any other questions? So what's the problem here? We have atomistic theory of matter. All the stuff about s orbitals and p orbitals and hydrogen this and all that. That's atomic theory of matter. And then we have me. Anytime you use me, you say you're using Maxwell's equations. Implicit in that, Maxwell's equations only work in the regime of continuous matter. Right? Okay. Now look. When you say refractive index, what are you really meaning? What are you really telling us? Well, I got polarizable atoms. Check. If I have an atom here, and the wave is going over here, there's a kind of a phase delay between excitation of this atom and this atom. Okay? Rayleigh does this, but not this. Rayleigh-Gans does both of these. Okay? But none of this other stuff. There's a time delay of oscillation. There's a phase. It takes a while for this guy to get moving once the wave hits it. It takes a while for it to get moving. Okay? And then what you have to do is you have to add these resultant scattering waves back into the incident wave. And you may even have to consider multiple scattering. And then you may have to have a certain geometry. The interesting thing about geometry is I make thin film measurements all the time. I can tell you if that sample is 25.1 nanometer thick or 25.2 nanometers thick. I can tell you that in some cases. So 0.1 nanometer, I can tell you, but guess what? Those are planar sheets, two-dimensional. You see, so dimensionality is a critical part of this problem. It may be that for two-dimensional things, I don't need the same type of machinery for a three-dimensional. If it's a little post or something like that. Okay. So what I'm trying to do is to come to universities and say, look, we have a problem. This problem is not a quantum mechanical problem. It is a 100-year-old, 200-year-old problem that was not solved because nobody back then had computers. Right? No one had computers. So what's our excuse today? Why are we using 200-year-old stuff when we're trying to generate nanotechnology? We shouldn't be doing it. But the thing is, we don't have the machinery. In this transition zone, we don't have the machinery. So I did my cheat. And you don't like it, I don't care you don't like it. I use it and it works. And in my mind, it's beautiful because it's so simple. What that means, however, is that when you get going to really get the nitty-gritty theory, that theory has to be beautiful as well. So, I've been thinking about scattering and who knows what the Olber's paradox is? Have you ever heard about it? He knows, of course. When you look up at night, why is the sky dark? More than 200 years ago, Olber thought of that problem, and it was a deeply profound question. Because at that time, everybody thought that the universe was infinite in extent. And if you have infinite in extent, wherever you pick, there will be a star somewhere there. Wherever you pick. There should be a point source wherever you pick. Because you can go out far enough, there will be a light source there. The night sky should be brilliantly bright. It is not. The Big Bang theory comes along and solves this problem. Why? Two reasons. Number one, the universe is finite. We don't have an infinite number of galaxies out there. Okay? And the second reason is the Big Bang says even if we did, the universe is expanding so much that at the fringes of the universe is expanding at the speed of light or faster. So even if there were stars beyond that, we couldn't see them anyway. So the so-called light cone would prevent us from seeing that. Okay, so that's what solved the Big Bang theory. The Big Bang theory solved Olber's paradox. One day in 1995, the director of the Hubble took advantage of his authority to do whatever the heck he wanted to do. And he says, I'm going to point that Hubble at the darkest place I can find. You're crazy, everyone thought. You're crazy to do that. Well, he found stuff, a lot of stuff. It took him 10 days focusing on that one spot. He found a lot of stuff. Later on, they picked a completely different spot. And this is called ultra-deep field because they use more time and better cameras. And if you wanted to download this whole thing, you could, and it's like 10 or 15 megabytes. You can download it, and there's something like 10,000 galaxies in here, all except this is not a galaxy. This is a star. We know that's a star because this is really diffraction of the camera of the telescope. This is a star. This is a star. There's a few more stars over here, but most of this other stuff are galaxies. So this is a star here. This is a star. See the diffraction? I don't quite understand the nuances of that, but that's a star. So this is a point source. These are not point sources over here. So my father his name is Rayfield Tsu. Everyone calls him Ray Tsu. He and Leo Isaki in 1970 something invented the superlattice. Who's ever heard of the superlattice? You know everything. You see, the thing about superlattice is, in physics, it's all about the periodicity. It doesn't matter that there's a silicon or a germanium atom there. What's important is the fact that you have periodicity. That's where all the wave functions come from. It's the periodicity. Who the hell cares if it's a silicon atom? That's irrelevant. That's physics. Dad and Isaki says, if that's true, put your money where your mouth is. I'm going to make a periodic structure with man-made periodicity. Gallium arsenide, indium gallium arsenide. Gallium arsenide, indium gallium arsenide. So that's what Dad did. They sent it to 4 journals, and every one of them rejected it. They all rejected that paper. And now they regret it because it has 5,000 citations or something, that paper. IBM, they were at IBM, decided to publish it in their own internal journal. So now it's one of the most cited papers. My dad is retired, and I called him up. So, it's like guys that are retired, he has some short-term memory loss, but I like to talk physics to him because that's where his core is. So, Dad, I got this crazy idea. It's like science fiction, but hear me out. I think the vacuum state is crystalline. So, what I'm trying to say is I don't think this picture should exist. I think this picture should be awash in light. Why are these dark? I don't get it. And it's not the Olber's problem. It's a scattering problem. This light has traveled 10 billion years to get to us. You mean in the time 10 billion years from there to here, you haven't scattered? So in my mind, the only way that's possible is because if you go to scattering theory, it's all about the structure factor. Okay? Anyone who does X-ray? Anyone does X-ray here? Okay? Okay. Are you a material? Do you do material science? Okay, but you've done X-ray, right? And they talk about the structure factor, right? And guess what? You don't get scattering unless you have order, right? If you have, so that's called Bragg diffraction. Bragg diffraction is scattering, right? So if you don't have periodic order, you have amorphous material, and every atom in there should scatter. That's amorphous scattering. Okay? So my idea is, why is it that this point is dark? I don't know. So I called up my dad and said, hey, Dad, I think that the vacuum state has crystalline structure. Because if it was amorphous, it would scatter like crazy. And if it was crystalline structure, there would be some Bragg diffraction or something, and we shouldn't, the light should just go straight through. Dad he wanted nothing to do with that. He says, Dave, you might be right, but I tell you what, I can't put that in my machine and measure it. You see, physics people like to measure stuff, right? And he's the type of physicist that would say to all those who do string theory, that is not physics, that is hocus pocus. So he called me, he says, Dave, that stuff that you're talking about is, it's like science fiction, it's not real. I was trying to get him to expand his imagination, but you know, you have to take that type of criticism and learn from it. So when you students, when you come up here and give a lecture, there are going to be guys out there who are going to chew your head off. And if you start pretending that you know the answer, it'll get worse for you. Believe me. Don't do it. If you don't know, say I don't know. And you will be a better person for that. But you have to learn how to handle a critic. My dad, just because he's my dad doesn't mean he's going to be nice to me. He's that type of physicist. So, in the back of my mind, I'm saying, hey, the vacuum state is not empty. We all believe in vacuum, in quantum mechanics. In quantum mechanics, there is no such thing as zero, right? Zero doesn't exist. Zero energy does not exist. It is impossible. Therefore, the vacuum should be filled with electrons and positrons, virtual. And the thing about virtual particles, when we talk about virtual particles, sometimes you get the feeling that, hey, it's just a kind of a mathematical trick to make the formulas come out right. They're not real. They're just kind of a mathematical trick. If that's the case, Stephen Hawking's whole life is for naught. You know who Stephen Hawking is, right? And he's the one who really predicted that black holes should evaporate. And how do black holes evaporate? By these electron-positron pair creations next to the event horizon. So I said, okay, what do I do? Well, you know, my mom used to say, television, turn that idiot box off. But these things are probably 1,000 times more idiot box than a TV is. Right, Mesut? So, out of every 100 things that I see, maybe one or two of them would pop up nice. And this is one of the things that did pop up nice. An article by Adam Mann. And he's talking about the measured Hubble constant. And there's a big problem. The European Space Agency, using the Planck satellite, measuring cosmic microwave background radiation, came up with one value. And the astronomers, using Cepheid variables, came up with another value. Cepheid variables are stars whose light intensity goes up and down. And the light intensity going up and down business is directly correlated to its intrinsic luminosity. If I measure the rate at this rate, it has this luminosity. If I measure it at another rate, it has a different luminosity. Therefore, it is a standard candle. So that's what the astronomers do. And you see this number is not equal to that number. And moreover, the error bars are such that there's no way to make this one equal to that. So another group said, okay, we have a problem here, but let's see if we can do another experiment. So instead of Cepheid variables, they use red giants. And you can see that this number is between that number and that number. Okay, I saw that, hey, that has potential. Let's see if I can make sense of that. Once again, the Hertzberg-Russell HR diagram. And I'm going to use the same parametric power law analysis. Like that. To define the wave number or the wavelength, I'm just going to go to the Hertzberg-Russell diagram. I know the Cepheids are F, or there's a whole range of F-related stars here. Okay? So our sun is here. This is our sun. Anyone who knows Spock from Star Trek, he's like a K-star over here. Okay? Therefore, the red giants are up there. They're sort of between an M and a K. These are red giants. So therefore, I know what their wavelength signature is. And I use that. And I fit the data with this power law of 4.0, so it's all Rayleigh scattering. I know it can't be anything more than Rayleigh scattering because these things are so tiny. It has to be Rayleigh scattering. Therefore, the power law has to be 4. And then in the meantime, I discovered there's even more folks using supernova. Now, these are the type of errors, 2% in their data, and the supernova guy is saying like 10%. These VBU, these are the places where astronomers define visible, blue, and UV. There's very little wiggle room in where this position is. Okay, this is that temperature, and therefore this is millimeter wavelengths. There's some wiggle room in where these are, the Cepheids, but not much. So, okay, not much. I can wiggle that around a little bit. Now, the only cheat in here is really where the supernova is. I don't know. And so I'm just saying, okay, they're probably in the UV band somewhere, and I just moved around, and whew, yeah, I got a nice fit, okay? So, the thing is, if you look at these error bars in here, this is pretty flat. This is pretty flat. All of a sudden, the error bar gets really big right where the Rayleigh scattering goes up hugely. So it's almost no wonder you guys are getting big errors because you're in the regime where there's lots of scattering. And therefore, you have to take into account of lots of different issues. Now, the thing about it is a lot of folks are getting really, really nervous about this. A lot of chatter about, oh, we need to define new physics. Maybe there's some dark matter, this or that affecting this or whatever. No. And the thing about it is because we have this fit over here, just like over here, we have this A term, and we have this HO term. So this A term, like I was telling you before, has a lot of information in it. In principle, this A term, and knowing the radius of the positronium, positronium has a Bohr radius of about twice that of the Bohr radius of hydrogen, because we're using not the mass of the electron, we're using the mass, reduced mass. So it has about twice the radius, so it's about 1 angstrom. So in principle, I know what all these terms are, and A is measured. So I should be able to find out how many positron electrons have been there that scattered the light from wherever it came from. The problem is this unit is kind of a crazy unit. The Hubble unit here is kilometer per second per megaparsec. It's like, geez, I don't know what the heck that is. I need a real astronomer to come back and help me. Okay, we have that. Let's go back and look at the original data so that we can convert this. But I tell you what, if we can convert that into a real number density of electron-positron pairs that light has interacted with, hey, that's real. In other words, that so-called vacuum has real stuff in it. Another thing you might say is, hey, maybe the astronomers didn't take into account all the scattering of known stuff. There's hydrogen, there's electrons in there, there's dust particles in there. But look, This is the bread and butter of astronomers. They know what they're doing. So I can have confidence that that point is correct. They know what they're doing. But the thing is, what they're not doing is they're not putting in stuff that they don't know about, right? They're not putting in what the vacuum state is doing. Because the vacuum state shouldn't be doing anything. But if the vacuum state is not doing anything, then there's no such thing as quantum mechanics. And we should all go home because we're wasting our time. So, in conclusion, I don't think that we need to develop any fancy new theories about what's going on. Every single team did the correct and proper measurement. These guys are right that this is where the real Hubble constant is, not because they were superior in their experimental capability. The capability of every team is comparable. They got it right simply because this is the long wavelength limit where there is no Rayleigh scattering. Okay? So, Rayleigh scattering is working fine. Quantum mechanics should be working fine. The thing that we don't really understand is the vacuum state. And that's where we need to have a lot of new work understanding what that is. All the stuff about dark matter, dark energy, it's all related to that. Okay? So you guys have a lot of work ahead of you. I'm getting too old for this, but you guys are young. You got a lot of work ahead of you. So in conclusion, thank you for listening to me to tell you ghost stories. Thank you very much.